All right, today we're going to talk about reaction energy diagrams, and this is the organic chemistry edition. So I'm going to have to draw for you an organic reaction, the one that we've already looked at, and we're going to start talking about how this plays into the energy diagrams. And there's some more complexity here than Chem 1 and Chem 2, your general chemistries, but it builds on that a little bit. So let me go ahead and draw those for you. All right, so here's the reaction we are looking at. Now, I'm going to start by talking about a simple reaction, and I want to label a couple of these things so we can also kind of look at them more simply. Now, I'm going to call this first reaction right here A, and I'm going to call this right here B, C. So essentially, A is the propene, B is the hydrogen, and C is the bromine. So in the first step, we have A and then we have BC bonded together. And in the second step, if you look, we have A bonded to B and we have C by itself. Now, why is this important? We're going to look at some more complexity in a minute, but I want to use this to talk about our first initial reaction energy diagrams. So let me go ahead and draw it for you. So if we look at increasing energy on the y-axis and we look at the x-axis being reaction progress, where do we start here? Well, we start with a fairly stable propene. So that's going to be something like right here, just making up a space here. And so we're going to start right there, and then we turn it into a carbocation. Well, what does this look like? Let me draw the reaction progress for you. At the beginning here, you have this propene and then you have this HBr. Now, what happens is as you break them apart, you're snapping that double bond, you're snapping that HBr. It takes a lot of energy to rip those apart. So we're going to get pretty high up here in energy. But then, as you notice right here as our product, you're going to have this carbocation. Now, where is that carbocation in energy? You notice the carbocation is quite a bit, if you look here, right? This is quite a bit higher in energy. This is a large change in energy here. This is a very endergonic, endothermic probably, but an endergonic reaction. It absorbs a lot of energy. And you learned that in general chemistry, that if the products are higher than the reactants, it's absorbing a lot of energy. It's more difficult to do that reaction. Well, the other thing you remember is that there's this other difference right here in energy. And what do we call this energy? What do we call this change in energy? Generally, this is called delta G double dagger, or the activation energy, the Gibbs energy of activation. And what is present here is called the activated complex. So the activated complex is kind of what is all in the middle. It's the highest point in that energy as you're breaking that BC bond and the propene and forming the AB bond. This activated complex is the least stable thing, right? It's the top of the hill where it's going to fall down one side or the other, right? This is where you've basically broken your HBr apart and you've broken your propene. You've almost formed your carbocation, and everything is sort of at the highest point of energy it needs for the reaction to progress. And so if we think about this, you are forming right now, well, at this point, at the beginning, you have A and you have B, C. And at the end, you have A, B, and you have C. So what do you have in the activated complex? At that moment in time right here, you actually have A, B, C. So you are partially formed the bond between A and B and partially formed the bond between B, or broken the bond between B and C, right? So I'm missing an arrow here. Let me show you that arrow. So this arrow here represents the bond breaking between H and Br. And this here represents that pi bond breaking and formation of the new bond. So all of that is at the activated complex point, those have all partially formed and broken, which organic chemists use a dotted line to refer to a bond that is partially formed or partially broken. That is called the activated complex. What do we call this point right here? Well, this we would call traditionally the product of a reaction. However, you'll notice this is actually not complete, right? That was step number 1, but we also have step number 2 yet to go. So we actually are going to call this, even though it is essentially kind of a product, it's going to be used for another step, so we're going to call this the intermediate. Now this intermediate, if you look, has a Br negative and a carbocation. And there's no bonds that are really breaking here. This is a very, very low activation energy because we don't have to do much. We have a positive and a negative and they want to join together. There's still a little bit of activation energy, but after a tiny bit of activation energy here, they essentially fall down. Now you're going to notice here that this is lower than the original. Breaking that double bond made things a little more stable. This makes the overall reaction favorable, right? So even though the intermediate is higher in energy, overall this reaction ends up being exergonic or exothermic. It releases energy, all right? But this first part took energy. And that first part took quite a bit of energy. Now, what is the activation energy of this whole reaction? I mean, don't we have another activation energy for our second step right here? Well, we actually do. However, it doesn't really matter. What matters is what we call the slow step. If you think back to general chemistry, you're going to remember that if a reaction has multiple steps, the slow step is the rate determining step because that is the highest energy overall. I like to explain it like this. If you were writing letters and you had people lined up and their job was to write letters, and one person's job was to stamp an address, the other person's job was to stuff the letter in the envelope, and one person's job was to write by hand, write each letter. The rate of the person stuffing, none of that matters. It's the rate of the person writing the letters that's going to determine the rate of the whole process. Because as soon as they're done writing it, it's going to get stuffed and mailed off in a second, right? So everyone else is going to be waiting on the person who's actually writing them. So that's the rate determining step. Just like here, our rate determining step is the formation of our carbocation. That's going to be our rate determining step. It's the highest in energy. So that's kind of how these reaction energy diagrams relate to these organic molecules. And you always need to visualize the bonds that are breaking and forming through the process, because that's what's going to help us understand how the energy relates to what's actually going on in the reaction. And we're going to need to apply this idea on several occasions, because the energetics will determine sometimes even what product we make when there's several different options. So we're going to get used to doing that pretty soon, especially already in the next reactions we're going to study